For any homework-related queries, call us at +1 678 648 4277. You can mail us at info@databasehomeworkhelp.com or reach us at https://www.databasehomeworkhelp.com. 1. Propose a relational schema for this database. Indicate the primary and foreign keys. Propose a reasonable set of functional dependencies for this schema. Show that your schema is in 3NF or BCNF. Solution: the following is one possible schema for the pet store database: customers, SID, name, address, CC hashtag, animals, aid, a name, species, breed, size, ownerid, orders, ordered, SID, order date, ship date, products, PID, type, species, color, price, quantity _ stocked, order _ info, ordered, PID, quantity. Primary keys are underlined. Foreign keys are in italics and are as follows: animals.ownerid references customer.sid orders.sid references customers.sid order _info.pid references products.pid order _info.ordered references orders.ordered. Functional dependencies are as follows: SID-name, address, CC hashtag a name, species, breed, size, SID. Databasehomeworkhelp.com. Orders-ordered, SID, order date, ship date, products-PID, type, species, color, price, quantity _ stocked, order _ info-ordered, PID, quantity. This is in BCNF since only primary keys appear on the left-hand side of any functional dependency. 2. Show the SQL for a query that computes all orders that are for a species of pet that the customer placing the order does not own. For the following questions, suppose there are 10,000 customers, 100,000 orders, 20,000 pets, 1,000 products, and 200,000 total products purchased. You may also assume that each row of each table occupies 100 bytes, each disk page is 1,000 bytes, and there is sufficient memory for any intermediate data structures, example hash tables, intermediate join results, to be memory resident. You may assume a uniform distribution of pets to customers, order to customers, products to orders, etc. Solution: this question is somewhat ambiguous. The queries shown here compute all orders that contain a product that is for a species of pet that the owner-customer placing the order does not own. They report the name of the customer, the order ID, and the type of the product that is for a type of pet the customer does not own. Databasehomeworkhelp.com. The straightforward way to compute this query is using a correlated subquery. Example, a subquery that references an expression in the outer query. Select distinct c.name, o.ordered, p.type, p.species from orders ASO, customers ASC, products ASP, order _ info ASINF, animals AS aware c.sid equals o.sid and INF PID equals p.pid and INF ordered equals o.ordered and p.species not IN. Select distinct species ASS1. All the species this customer owns from animals where c.sid equals animals.ownerid. We can get rid of the correlation in the subquery as follows: select distinct c.name, o.ordered, p.type, p.species from orders ASO, customers ASC, products ASP, order _ info ASINF, animals AS aware c.sid equals o.sid and INF PID equals p.pid and INF ordered equals o.ordered and c.sid p.species, not IN. Select distinct customers.sid, species ASS1 from animals, customers where customers.sid equals animals.ownerid. Databasehomeworkhelp.com. We'll assume the second query is the one to use. Note that when the query is rewritten in this way, it's clear we don't actually need the reference to customers in the inner query at all. Select distinct c.name, o.ordered, p.type, P.species from orders ASO, customers ASC, products ASP, order_info ASINF, animals AS aware C.sid equals O.sid and INFPID equals P.PID and INF orded equals O.orded and C.sid P.species, not IN, select distinct ownerid, species ASS1 from animals. 3. Propose a set of index structures for this query that you believe would be a good choice for making it run efficiently. Solution: when there is abundant memory, indices don't help. Look at the plan in Figure 1, which is the solution to problem 4. Each of these joins is a key foreign key join, and hence produces an output equal to the size of the larger, primary key table. In some cases, we could use a primary index on the inner relation to efficiently look up join results, but in general we would have to do a very large number of index lookups, since each tuple in the inner relation always joins with at. databasehomeworkhelp.com. Least one tuple in the outer relation. These index lookups would tend to be random. To avoid this random I/O, a better choice would be hash or merged joins with hash tables built or resorting done on the fly. With sufficient memory, these data structures allow us to sequentially scan each inner relation just once in sequential order. No indices are needed. databasehomeworkhelp.com. 4. Show an efficient equivalent relational algebra for this plan, in a tree-structured representation. For each node in the tree, choose a particular implementation of the operator in question. Indicate which indices are used or as well as the use of sargeable predicates as needed. Solution: see Figure 1. There are only 3 join orders of interest for the left subquery. We could start by joining products to order_info, orders to order_info, or customers to orders. The correct choice is the ordering that minimizes the number of tuples along each arc. Since any join that starts with order_info would immediately put 200k tuples along each arc, we should start with the customers/orders join, which only produces 100k tuples. We continue in a left deep fashion since that allows us to pipeline the outer relation, without hashing/partitioning it, since we have sufficient memory to hold the hash on the inner in RAM, arriving at the join ordering shown here. There is only one possible ordering for the right plan. 5. Estimate the number of random and sequential disk I/OS that would be required to compute the result of this query plan. Show your work. Solution: as noted above, the plan shown here has to sequentially scan each. databasehomeworkhelp.com. Relation once. There are 10 tuples per page. Hence, we have to perform the following I/OS, customers, 10k/10 equals 1k I/OS orders, 100k/10 equals 10k I/OS pets, 20k/10 equals 2k I/OS products, 1k/10 is equal to 100 I/OS order_info, 200k/10 equals 20k I/S total, 33, 100k sequential I/OS. 6. Suppose there is only 1 megabyte of memory available for intermediate data structures. Would this affect your plan choice? Re-estimate the number of sequential and random I/OS required. Solution: 1 megabyte of memory is enough to hold approximately 1,000 pages of data. We have 4 join operators. Let's assume we divvy these pages up evenly between them, hence, there are 250 pages of memory per operator. For all of our joins except products with order_info, with products as the inner, we will need to use an external join that writes some data to disk. Recall from Shapiro that as long as we have SQRT, relation size, pages of memory, we can compute an external hash join in at most 3 sequential passes over the data, 1 to read, 1 to write out hash partitions, and 1 to process each of the hash partitions. The largest relation is 20,000 pages. 20,000 (1 divided by 2 is equal to